Hello, today we want to explain about solving differential equation using eigenvalue and eigenvector. We are from group 7. Our team consists of 4 people, which is Aliatul Hanan, Afrina, Wan Anis and Yasmin. For the application, we choose the application on population growth. So let's we discuss together. Before we go deeper into this topic, let we know what is the meaning of population growth. Population growth is the study of how the number of individuals in a population increases or decreases over time. Mathematically, population growth is commonly modeled using differential equation, which describe the rate of change in population size over time. Eigenvalue and eigenvector used to analyze the stability of equilibrium point and determine whether population will stabilize, oscillate, or collapse. For a real-world example, we choose the steady-state analysis of population movement.
In two cities, Seattle and Portland, people migrate between the cities every year. Each year, 5% of Seattle population move to Portland and 20% of Portland population move to Seattle. If both cities start with 500,000 people, what will happen to the population of both cities in the long run? Will they reach a steady state distribution? Now we want to construct metric A. Metric A is constructed based on the movement of population between Seattle and Portland. According to the problem, 5% of Seattle population move to Portland each year, while 95% stays. On the other hand, 20% of Portland population move to Seattle and 80% remain. So this information used to form a 2 by 2 Markov metric. So for metric A, we have first row which is 0.95 and 0.2. Meanwhile, second row we have 0.05 and 0.80. We are told that both Seattle and Portland start with 500,000 people, so the initial state vector is 500,000 and 500,000. Now, we want to find the eigenvalues of metric A. So, we will use the formula determinant of A minus lambda I equal to 0. So, we subtract lambda from the diagonal element of A and compute the determinant. So, the matrix become, for the first row, 0.95 minus lambda, 0.20. Second row is 0.05, 0.80 minus lambda equal to 0. Then we solve all the calculation and we will get lambda 1 equal to 1 and lambda 2 equal to 0.75. Then we want to find eigenvector for every lambda. For lambda equal to 1, we substitute this value into the expression A minus lambda I. Then we substitute all the value into the expression and we will get negative 0.05, 0.20, 0.05 and negative 0.20. Now we want to find a non-zero vector such that A minus lambda I x equal to 0. So we write the metric equation. And we divide both x1 and x2 with 0.05. And the final answer, we get x1 equal to vector 4, 1. For lambda equal to 0.75, we do all the same step that we do just now. And the final answer that we get is 1 and negative 1. Then we want to find the diagonal metric of eigenvalues. So we will use a formula D equal to P negative 1 AP. So first step, we will find the inverse of metric P. So inverse metric P that we get is 1 over 5 multiplied by the metric first row 1 and 1, second row is 1 and negative 4. Then we want to find the multiplication of A and P. The final answer that we get is 4, 0.75 and 1, negative 0.75. Now we multiply the inverse of metric P with the result that we get before. So the final multiplication gives us diagonal metric which is 1, 0, 0 and 0.75. Next, we want to find the population after k years. We use the formula x subs k equal to PD to the power of k multiplied by P inverse and x initial. So we begin with multiply the P inverse with the initial population, which is the vector of 500,000 and 500,000. Then we apply the diagonal metric, which is d to the power of k, to this transform matrix. The final answer is 200,000 and negative 300,000 times 0.75 to the power of k. Finally, we multiply the result with metric p to return the vector back to the original basis. Now we find the population at the steady state. Steady state happens when k equal to infinity. So we substitute infinity into k to observe the long run behavior. When we do that, the term involving becomes 0. As a result, the final population vector becomes 800,000 for Cyril and 200,000 for Portland.
Result and discussion. Interpretation of result. The results showed that the steady-state population distribution between Seattle and Portland is 800,000 in Seattle and 200,000 in Portland. This means that over time, despite both cities starting with equal populations, the migration patterns lead to a situation where Seattle gains a larger share of the population. The steady state was obtained from the eigenvector corresponding to the eigenvalue of 1, which represents the stable population distribution in the long run. The analysis shows that Portland's population decreases to 200,000 while Seattle's population increases because a higher percentage of people migrate to Seattle each year. This leads to a final distribution where Seattle has a much larger share of the total population. The eigenvalue of 1 indicates that the system will eventually reach a stable equilibrium where the population distribution does not change over time, while the second eigenvalue of 0.75 shows that the system will converge towards this equilibrium fairly quickly without any oscillations. However, it is important to note that this model assumes fixed migration rates every year and does not include factors such as births, deaths, or even unexpected changes in migration patterns, which may affect the accuracy of the predictions in real-life situations. Overall, the eigenvector method is useful as it clearly shows both the final stable population distribution and how fast this distribution is achieved over time.
For conclusion, population growth and migration can be effectively modeled using mathematical tools like differential equation and linear algebra. For example, let's consider the cities of Seattle and Portland. Each year, 5% of Seattle's population move to Portland, while 20% of Portland's population move to Seattle. We can model this situation using a system of equations that describes how the population change over time. This leads us to a steady state solution where the population of both cities eventually stabilize, even though people continue to move between them. By analyzing the system using eigenvalues and eigenvectors, we can confirm that a stable equilibrium exists. Interestingly, in the long run, Seattle ends up with a larger population than Portland, not because it starts out larger, but because a greater percentage of people move into Seattle each year than leave it. This example shows how migration patterns, not just initial conditions, can strongly influence long-term population distribution.